Hello, everyone. I'm Shafi Goldwasser, and I'm extremely pleased to introduce Craig Gentry, who is going to talk about homomorphic encryption. Craig is currently the Chief Technology Officer in TripleBlind, a startup that specializes in applications of privacy-enhancing technologies, of which homomorphic encryption is a very important technology. And Craig proved in 2008 this amazing result while he was still a graduate student at Stanford, and that is he proposed the first fully homomorphic encryption scheme. The existence of such scheme was conjectured or was asked as an open question 30 years before that. And I think that if anybody had to bet on it in the field, it was that it does not exist. And yet in 2008, Gentry came up with the first scheme, and since then it's all history. There has been a tremendous development of more and more efficient homomorphic encryption schemes based on weaker and weaker assumptions. It is the really solution for cloud computing, a lot of collaborative computing, where you want to maintain the secrecy of your data, and has really opened the door to a next generation of cryptographic type methods where you can do very fine-grained hiding of information. You can compute on hidden information and more. And, you know, I am at awe of what Craig has achieved. And I'm very pleased to introduce you to his talk on homomorphic encryption.
Okay, thank you. I'd like to express my appreciation for being invited to give a talk at the ICM. My goal for the talk is that it's lightweight and encouraging enough so that you feel like you can, you know, if you want to try, you can try to build a new homomorphic encryption scheme. And I hope that you actually come up with a new one because we're kind of stuck on the same framework. All the schemes look sort of the same. So if a mathematician comes up to me and says, why didn't you just do it this way? It's really simple. That would be ideal. On the other hand, I don't want to cause overconfidence. So I'll try to give you enough detail to avoid that. Okay, so homomorphic encryption is first of all about encryption. So this is the encryption scenario. You have Alice and Bob, of course. Alice here wants to send a message to Bob, but she's worried about malicious eavesdroppers on the line that might intercept and read her message. Okay, so what she wants to do is encode her message in a ciphertext, which is like a little box with a lock on it, such that only Bob can unlock or decrypt the message with his key. What you want in terms of correctness is obviously that if you encrypt a message and then decrypt it, you should get back the same thing. And in terms of security, I'll get into more detail later, but the ideal is that the ciphertext should hide all partial information about the message. So the adversary looks at the ciphertext, he learns nothing at all about the message, like not any individual bits or any function of the message, nothing. Homomorphic encryption is secondly about computation. So there are various different models of computation. You have Turing machines, you have random access machines, which are kind of like regular computers. You have Boolean circuits, you have quantum computers maybe. So we're going to focus mainly on Boolean circuits. This is what a Boolean circuit looks like. It has gates. Usually they're and or not gates, that sort of thing. But you can arithmetize everything so that they're basically addition and multiplication gates. So you might imagine the input here being a bunch of bits, zeros and ones. And then you do some additions and multiplications and it spits out a bit at the end or several bits. Okay. And basically you can do general computation of Boolean circuits. So basically anything that you can compute efficiently, you can compute efficiently with a Boolean circuit. Because this is the way your computer works, basically. It just does these sort of Boolean operations inside. Nowadays, it's a little more complex, you know, the processors that they use, but this is the basic idea. So back in 1978, sort of around the dawn of modern cryptography, right after the invention of RSA, these guys, Revest, Edelman, and Drutuzos, said, can we put encryption and computation together so that they kind of play nice with each other? So the idea would be that you could encrypt data and do computations on the data while it's encrypted. I mean, normally in an encryption scheme, you encrypt it. It just sort of sits there. It's a blob. It's a random looking blob. You can't do anything with it except maybe decrypt it, and then you can do stuff with it. But their idea is, well, what if we could just do the computation on the data while it's inside the encryption? That would be really useful. So their vision is secrecy and processing living together in perfect harmony, and it's to be sung in the tune of Ebony and Ivory. Okay, so so here's kind of an elaboration of that scenario. You have Alice here, who wants to use cloud computing, right? She doesn't want to store all of her data on her phone, right? She wants to be able to put her data out on the cloud, but she still wants her data to be useful, right? So, but she doesn't want the cloud to learn her data also. So what does she do? She encrypts her data. She stores that out on the cloud. And then at some later point, she has a query about her data, like, send me all the files with some keyword in them, right? So that's some function F. This could be encrypted too. And what we want is that the server, that the encryption scheme has some algorithm eval that the server can use, that it can plug in F, the function F, and it can plug in all of that encrypted data and run this magical eval algorithm, and it'll output an encryption, a ciphertext that encrypts the result of F being applied to that data. So an encryption of F of M. Okay. And then the cloud just sends that back to Alice, and she can decrypt it. She gets the result that she wants. She gets all the files with that particular keyword. Now, in terms of security, what we want is that the cloud learns nothing about the messages, right? That's kind of the whole point. It can run this evaluation algorithm obviously without decrypting the individual ciphertext, and it doesn't learn anything at any intermediate point during this computation, okay? Even the message it sends back to Alice is encrypted. It's encrypted throughout. And what we want in terms of efficiency is that the amount of work that Alice does should be small. I mean, what does she do here? She encrypts her initial data, and she has to decrypt the ciphertext that comes back from the server. So her work shouldn't depend at all on the complexity of the function F, aside from the fact that, she decrypts this output of the function F. It shouldn't depend on the actual computation of F. Otherwise, it's not really a delegation scheme, right? She would basically be doing all the work herself. So some other applications, I mean, there are many different settings in which this is useful. You can imagine private tax preparation. I don't know why, I'm from the US, so I give this example, and people don't know what I'm talking about because tax preparation is usually pretty easy. But in the US, you have accountants that you send your financial information to, and they output a tax form for you that you can file with the IRS. So maybe you don't want your accountant to know all your financial information. Why should he? You just want the tax form, right? So you want to be able to encrypt all of that information, have the accountant compute your encrypted tax form, which you decrypt, and the accountant learns nothing. Sort of more on the serious side, you could do private genomic analysis, private machine learning. You can imagine that there are privacy implications for these sorts of things, although they're very useful. Genomic analysis is very useful to researchers to learn about diseases. So in some circumstances, we would like to allow researchers to have that data, but not just dumped in the clear. We would like it encrypted in a way that it can be analyzed under the covers, so to speak, until that maybe they can decrypt some final result that sort of distills the information that they wanted to get. So does homomorphic encryption seem impossible? Actually, it makes sense even in the physical world. So I have a physical analogy for you for this. This is Alice's jewelry store. So Alice owns a jewelry store and she has precious materials, gold, diamonds, and silver. And she wants her workers to sort of process these materials to make rings and necklaces out of them, right? So this is what they do. Boop. And but she's worried about theft, right? She doesn't want to, give the workers unfettered access to all these diamonds, right? So what does she do? How can she allow her workers to process the raw materials without giving them access? Well, I assume this is what they're all using in the diamond industry and everything. So what Alice creates a locked glove box, and she puts the materials inside and locks it. And then the worker can come and stick his hands inside the gloves and make the ring or necklace. But let's assume that this box and even these gloves are impenetrable. So he's like, okay, I'll just give it back to Alice. And then Alice unlocks the box to get the final result. So this is kind of what homomorphic encryption is doing. Having learned category theory and as an undergrad, Alice can even draw this commutative diagram that basically you can go in either one of two directions, starting off with the precious materials locked inside the box. I mean, either you can just unlock them and produce the ring in the clear, so to speak, or you could go the other direction where the worker has to work inside the box and Alice decrypts the result after it's done. Of course, Alice prefers the latter because this is what provides her security, right? So this is not just a simple homomorphism. There's also kind of a security aspect. So you need that the downward direction here is hard, in some sense yet to be defined. And the rightward directions are easy. Okay. So in terms of homomorphic encryption, this is what it looks like mathematically, the commutative diagram. So going downward, of course, you have decryption from the ciphertext level to the message level. And then you can imagine that F is some processing function that operates on data that's in the message space, which could be a circuit of additions and multiplications. And what you want is that you have this evaluation algorithm on the top that can do analogous operations while the data is encrypted. Okay, and it's a commutative diagram, so it doesn't matter which way you go, you should get the same result. And as before, the downward direction is hard and the rightward direction should be easy. Okay, so basically homomorphic encryption combines two ingredients. First of all, the homomorphism, which you're probably more comfortable with. And secondly, security, which is this, which I haven't really defined properly, but basically that there should be some notion of hardness in the decryption direction. So why doesn't a ring homomorphism work? So that's kind of the obvious thing to try if you're just starting with the idea of a homomorphism. So, so here's your ring homomorphism. You have, it can do addition and multiplication operations. And at the top, you would have the ciphertext. This delta here would be the decryption function. Decryption is a ring homomorphism. And there you have, those would be the messages. And as I said before, addition and multiplication are complete for general computation. So you can do any computation on the data while it's encrypted in the scheme. But the question is about security. So there's no known way to make such the ring homomorphism based scheme both secure and efficient. So so one problem is that encryptions of 0 form an ideal in this ring, right? And you really don't want to reveal even whether a ciphertext encrypts 0, okay? Because 0 pops up a lot. So in a homomorphic encryption scheme, if you can detect whether something encrypts 0, you can also detect whether two ciphertexts encrypt the same thing by subtracting one from the other. That's not very good. And also, just as a practical matter, in homomorphic encryption, you do things like compare operations. You want to compare whether two things are equal or not. And usually the result of that operation is a bit, 1 indicating they're the same, 0 that they're not. So you're going to have encrypted bits, which are often 0 a lot of the time. And if you can detect those encryptions of 0 easily, that would be bad. So we need the ideal membership problem in this ring to be hard. Okay, it can be hard in some cases, like for example, infinite polynomial rings, where basically you have a bunch of polynomials and the question is whether yet another polynomial is an ideal generated by the initial polynomials. Okay, so that problem seems hard, but infinite polynomial rings aren't really great for cryptography because we don't have infinite storage space, right? We want the system to actually work on a computer. And if you imagine starting off with some initial ciphertext in an infinite polynomial ring, and you add and multiply and add and multiply and add and multiply, those ciphertexts are going to get pretty big pretty fast. And we don't want the ciphertext to grow in an unbounded way, because that's just not practical. On the other hand, the ideal membership problem, when you're talking about smaller rings where maybe the ring elements have compact expression, in that case, the scheme is usually not secure because, I mean, often the encryptions of 0 are just literally an additive subspace of the total set of ciphertext. And so it's very easy using linear algebra to detect whether something is an encryption of 0 or not, just by seeing whether it's in that subspace. So this is not exactly a proof that there's no way to use a ring homomorphism to do homomorphic encryption. It's just that I haven't seen any promising leads here. So I'd be interested if you have any ideas. So looking ahead to the actual solution that I'll describe after this. So the diagram looks kind of similar superficially. You have the ciphertext and the messages and you do addition and multiplication operations, but it turns out that C is not even a ring here. And the box plus and box times operations are not even associative. So they're very kind of messy and complex operations. So in fact, if you looked at C, it's kind of the minimally structured item in this box, both with respect to addition and multiplication. So it just seems that security requires the ciphertext space to be less structured than just a ring. Okay, yeah, maybe not, but that's just what it seems like at the moment. Okay, so now I'm going to jump into the, oops. Oh, sorry. So I'm going to go into a little more detail about what it means for an encryption scheme to be secure, because maybe this is the part where your average mathematician who's not a cryptographer needs more detail. So let's start with public key encryption. What does public key encryption look like? So first of all, Alice generates a key pair. So there's an encryption key and a decryption key. Sometimes the encryption key equals the decryption key. So that's like a lock that maybe you have to use the key to even lock it. But public key encryption is a situation where you don't even need the key to lock it. So after you send the encryption key to some other guy, he can use that to lock, to encrypt. And the encryption formula takes the encryption key, maybe some randomness, and the message, and outputs a ciphertext. And that goes to Alice. And then Alice uses her decryption key to decrypt. And you have the usual correctness condition. So what does it mean for an encryption scheme to be secure? So the weakest notion of security is that you can't recover the message from the ciphertext. You want at least that. Maybe the strongest notion of security is that you learn nothing about the message from the ciphertext, except an upper bound on the length of the message, because it has to fit inside the ciphertext, right? So, okay, that part's unavoidable, but nothing else. So Shannon was sort of started modern cryptography by rigorously defining what it means for an encryption scheme to be secure. He defined perfect secrecy, where it's exactly that. The attacker learns nothing at all about the message. But then he also proved that the only solution to the only scheme that meets this rigorous demand is the one-time pad. So in the one-time pad, Alice and Bob share a random key that's at least as long as the message. And they just sort of add that key to the message. And then, the other side just subtracts it off, right? So from an outsider, since that key is completely random, of course, the ciphertext looks completely random if you add together things in the right way. So, but that's the only way to meet this, this requirement of learning exactly nothing about the message. So what can we do in more practical settings, where we want a short key, a key that's maybe much shorter than the message that we're encrypting, and we want to reuse that key to encrypt lots of different messages? Goldwasser-Macaulay showed that there's a rigorous way of defining basically a very similar notion in this context, where called semantic security, where a computationally bounded attacker will learn basically nothing about the message. Of course, the information will be there if you encrypt lots of different messages with the same short key. Eventually, there will be enough information there that in principle, you could figure out the unique key that encrypts all of these individual messages. The information is there. The question is whether any reasonably computationally bounded attacker can figure out anything about the message from all of those ciphertexts. So for the particular case of when the message is just 0 or 1, a bit, their notion is equivalent to this, that basically you're given the encryption key, so you can produce as many encryptions of 0 and 1 as you want. But then I challenge you by giving you an encryption of 0 or 1. I don't tell you which, and you have to guess which bit I encrypted with probability significantly better than 1/2, right? If you can't, if there's no efficient algorithm that can distinguish what is encrypted in this challenge ciphertext, then we say the scheme is semantically secure. So just to put a little picture to this, so you have the set of ciphertext, which and the set of messages, and downward, of course, you decrypt. And you can view encryption as kind of a sampling algorithm that samples from the set of ciphertexts, samples from the preimage of the message that you're trying to encrypt, right? So we want a scheme that works when the messages might just be only 0 or 1. That might be the only 2 messages we have in our scheme. And so we have some ciphertext up here, which are the preimages of 0 and 1. And you can see that to meet this definition, the encryption scheme has to be probabilistic. There have to be many ciphertext per message, because I'm giving you the encryption key, So you can produce an encryption of 0 and 1 yourself. And if there's only one encryption of 0 and one encryption of 1, then of course I can easily tell whether the challenge ciphertext in my hand is the same as one of those 2. So there have to actually be a lot of different ways of encrypting each message. Okay, but what does this part mean? Indistinguishable by efficient algorithms. So for that, we have to get into computational complexity. So here's a simple example. So we think of multiplication as kind of an easy operation. Maybe not if you're in elementary school, but for computers, it's pretty easy. So you can you can take a bunch of prime numbers together and you can multiply them together to get some natural number. But then in the other direction, you have factorization, which is trying to figure out the prime decomposition of an integer. So multiplication, as I said, seems pretty easy. And to formalize what it means to be easy, what I mean is that the complexity of multiplying 2 n-bit or n-digit, if you prefer, numbers has time complexity n² if you do the simple grade school method of multiplying numbers. Or if you want to get fancy, you can do it in n log n time. And so we say that's polynomial time because n squared and n log n are polynomials. And so polynomial time means that the complexity of the algorithm is polynomial in the number of bits of input. So the input here are the two n-bit numbers. On the other hand, we think factorization is hard. We don't know for sure, but the best algorithm we have now is the number field sieve, which has this complexity for factoring an n-bit number. So that's kind of a weird number. It's if it were e to the n, that would be exponential time. And if it were e to the O of log n, it would be polynomial time. So it's kind of in between those two. So it's super polynomial sub-exponential time. Okay. So in general, computational complexity classifies problems by the resources needed to solve them. So on the left-hand side, you have P, which are the set of problems that are solvable by an efficient algorithm. Running time, polynomial in the problem's input size. So multiplication is an example of that. On the other hand, you have NP, which is a set of problems whose solutions can be verified by an algorithm in P. NP doesn't mean not P, okay? In fact, it shares a lot with P in the sense that if you have a solution, it can be verified efficiently. So that's good, but that doesn't mean you can find it efficiently necessarily. So by algorithm, I just mean, well, traditionally a Turing machine, but nobody uses Turing machines. So you might just think of a regular computer or by hand, the number of steps it takes you by hand to do this. And of course, major conjecture is that P is not equal to NP. So what about breaking public key encryption? Is it in P? Is it in NP? Well, it's definitely in NP because if we guess the randomness used to encrypt the message, we could just try to plug that into the encryption procedure function and see if we get back the ciphertext that we have in our hand. Hopefully it's not in P. I mean, we hope that the best breaking algorithm should take at least super polynomial time, preferably exponential time. And that's what we mean by we want indistinguishability by efficient algorithms to get semantic security. So it becomes clear that public key encryption exists only if P is not equal to NP, which is this big unproven assumption. If someone proves that P is equal to NP and actually has an efficient algorithm, that would be pretty devastating for, I don't know, the world economy. So that's a big unproven assumption there. So we don't have, because of that assumption, we don't have absolute security for public key encryption schemes. But we can still prove something. We have relative security. We can try to prove our schemes secure relative to a natural, plausible computational assumption, like factoring. So for example, if we could prove that if you can break my crypto system, then you can factor numbers efficiently, that would be pretty cool. So that's the sort of thing that we try to do in cryptography. So this is a reduction between two problems, and basically what's happening here is that you build a reduction that where the factoring algorithm takes some number to factor. And if you've proven a reduction, then that factoring algorithm sort of queries the crypto system breaker, uses it as a subroutine, gets some output back, and that output helps it to solve the factorization problem. So you can prove reductions between problems, and that's the way that we try to prove that crypto systems are secure, by basing them on problems that we are pretty confident are hard. So besides factorization, what other computational assumptions are plausible and natural? So one direction is lattices. So lattices have proven to be very useful in cryptography over the past few years. And what a lattice is just basically a big grid in space. So it's you have some basis vectors that are linearly independent. These basis vectors describe the types of hops in space that you can make. And the lattice points are all the points in n-dimensional space that you can reach by doing these different types of hops. Okay, so here's one hop that you can do, for example, b1 minus 2b2. Now there are various different hard problems that you can define over lattices. One is the shortest vector problem. Find the shortest non-zero vector in the lattice given a basis. So if you're given a really nice orthogonal basis, maybe it's pretty easy, at least in 2 dimensions. But if you're given a really skewed basis in 500 dimensions, it's not so clear how to take those initial basis vectors that you're given and find the shortest lattice vector. Yeah, so here's the shortest lattice vector here. Okay, and then we can have a relaxation of that problem, which is the alpha approximate shortest vector. Find a vector at most alpha times the shortest non-zero vector. So that actually still seems really hard in a high number of dimensions. In fact, the best known algorithm for alpha approximate SVP, which has been looked at by some mathematicians over the years, is an algorithm that takes 2 to the n over log alpha time. So just to give you an example, it takes about 2 to the square root of n time to compute a 2 to the square root n approximation of the shortest vector problem. So it seems like a really hard problem. So we would like to base cryptography on that. That sounds great. The problem is that the shortest vector problem is a worst case problem. So, normally you can prove, for example, the NP completeness of the shortest vector problem using randomized reductions for the finding the actual shortest vector. But NP completeness is kind of a worst case criterion. It basically says that there's no efficient algorithm that's going to efficiently solve all instances. What we need for crypto is that there should be no algorithm that works on random instances. So for example, I'll choose my key randomly, you'll choose your key randomly. It would be bad if I had a pretty good percentage, 1% of the time, even I could figure out what your key is based on the ciphertext. Okay, so it has to, what we want is that there's no algorithm that performs reliably on random instances, not just a few worst case instances that we can hardly even find. Okay, so what's cool about lattices is that we have worst case to average case reductions. So ITI showed that actually alpha approximate SVP, in the worst case, if that's hard, then he described a modular lattice problem that has that's hard on average. And Regev did something similar, where he showed that if alpha approximate shortest independent vector problem, which is related to SVP, is hard for quantum computers, then the problem he defined, learning with error, is hard on average. So we don't have a great understanding of quantum computation, but people, smart people have looked at this and tried to figure out how to break various lattice problems with quantum computers. And nobody has found anything yet. So we're kind of confident that these lattice problems are hard even for quantum computers. And if you believe that, then learning with error is hard on the average. Okay, and then he actually defined a very simple crypto system, which I'll get to in a second, based on learning with errors. And he showed all of these reductions that, if you can find an efficient break of his encryption scheme, then you can solve LWE, which means in turn, you can solve the shortest independent vector problem with a quantum computer. Okay. Oops. So here is the learning with errors problem. So basically, what you do is you fix a small parameter, epsilon, which I'll call the noise parameter. And I'm going to give you a bunch of linear polynomials. They'll have small coefficients that are in the range -1 to 1. And your job is to distinguish which world we're in. So case 1 is that these polynomials are all uniformly random. And case 2 is that there's some secret S, such that basically when you evaluate all of these polynomials at S, they evaluate to something very close to even numbers. So that's what this notation means, that if you evaluate all of these ciphertext polynomials at S, you get, sorry, the M should be 0 here. You get 2R plus E. In other words, it's very close to an even number. 2R is an even integer, and the epsilon is some very, very small error. So that's the learning with errors assumption. Again, so either the ciphertext polynomials are completely random, or they have this special property with respect to some secret that you don't know. That if you evaluate it at that one point, all of the ciphertext polynomials have in common that they evaluate to something that's very close to an even integer. And the closeness is defined by this value epsilon. Okay. Epsilon could be super small, in which you're almost precisely even integers, or it could be more relaxed. And then his encryption scheme, you know, basically ciphertext look like these polynomials that I just described in the LWE problem. So you have some secret key, which is just a 0, 1 vector. And if you want to encrypt a bit M, basically, I'm not going to tell you how the actual encryption process works, but the ciphertext has the form that it's a linear polynomial that when evaluated at the secret key, it basically equals the message M mod 2 up to this epsilon error, right? So if M is 1, for example, then C evaluated at S will be an odd number plus some small error, okay? All right, so now let's try and add and multiply these ciphertexts. That's what we're trying to do, right? Homomorphic encryption. So we want to be able to add and multiply these things and preserve the messages inside, basically. So let's see what happens. So first of all, if epsilon is 0, it works great. So it's just a perfect ring homomorphism, right? So in this case, you know, if you encrypted 1, C of S is actually literally an odd integer. If you're encrypting 0, it's an even integer. Everything works nice. It's a ring homomorphism. So that's great. You know, there's some problems. First of all, the degree increases as you multiply ciphertext. So that's an issue for efficiency. And for security, it's not secure with epsilon equals 0, because you can solve this using linear algebra, because you have a bunch of exact equations with respect to the secret key, exact linear equations. All of these C's are linear ciphertexts, linear polynomials. So, okay, fine. Let's reintroduce the error epsilon. And let's try to do an addition. Let's see what happens. Well, everything is preserved modulo 2. The only thing we have to worry about is the error. The error, you know, if the errors of the initial ciphertext were of size epsilon, you add 2 of them together, the new error could be of size 2 epsilon. So the error grows a little bit. What about multiplication? So if we multiply 2 ciphertexts, things get pretty hairy. So we multiply this, we multiply the 2 ciphertext polynomials, and then we actually expand everything out. So M again is the message, and R is an integer, and the E's are values that are small noises that are supposed to be of magnitude less than epsilon, right? So what do you get? Well, you get M1 times M2. Well, that's good, because you want the new ciphertext to encrypt M1 times M2. And then you get some even stuff, which I've grouped in the 2R. And then you get the error part, which is E1 multiplied by the second ciphertext, C2 evaluated at S, and then E2 times C1 at S. Okay, now we actually have to be concerned about the magnitude of like C1S and C2 at S. So what is the magnitude? Well, to make it as small as possible, what we should do is, first of all, just make sure if the coefficients of C1 and C2 are not already in the interval -1 to 1, we should put them there by reducing them modulo 2. If we translate any of the coefficients of C by an even integer, it won't affect the final decryption result because S is integral. So it'll preserve everything mod 2. It won't even affect the error. So we can just reduce the coefficients of C modulo 2 into that interval, and everything will be fine. And that makes them as small as possible. In that case, since S has coefficients that are 0 or 1, C evaluated at S will have magnitude at most n+1. Okay, so what that means is that at the end, the size of the error is going to be at most 2 times n+1 times the original epsilon. Okay, so that's a little concerning. The noise grows considerably more than for addition. And this polynomial is now quadratic instead of linear. We want linear polynomials. And the precision is all messed up. I mean, I didn't really mention this, but of course, when we have the coefficients of C, we maintain a certain amount of precision. We're not keeping arbitrary precision because that's not efficient. And at the end of the multiplication, we want to sort of truncate back down to that precision that we maintain along the way. And so when we truncate that precision, that's going to introduce some more error to this equation. I'm not going to address exactly how much. I'll just say for that part, it's pretty small. But what about the fact that the ciphertexts are quadratic now? What do we do about that? Well, we have to introduce publish some more polynomials into the scheme to basically help the evaluator reduce ciphertext polynomials from quadratic back down to linear. What do these polynomials look like? Well, they're quadratic polynomials, and they have basically only one quadratic term. The rest is linear. And they're all kind of like encryptions of 0. You know, an encryption of 0, a ciphertext that encrypts 0 as the form C of S is kind of equal up to epsilon 0 modulo 2. So these are just like that, except these are quadratic polynomials instead of the normal linear ciphertext polynomials. Okay, so they have these kind of weird properties, and the idea is that if you have a ciphertext polynomial that has become quadratic because you just multiplied together two ciphertexts, you look at all the individual quadratic monomials and you say, hey, I'm going to get rid of you using this Qij by subtracting off the right multiple of Qij, right? And I'm going to, and you have another Qij for this monomial, and you just keep subtracting off all the quadratic polynomials until you're back down to a nice linear ciphertext polynomial, as it should be. This also increases the noise because all of these, of course, we can't give exact equations in S. All of these polynomials have this, are noisy also. So when you subtract off all of these multiples of the Qij's, that also introduces more noise, which we have to worry about. And it gets a little worse. It also changes the security assumption. So before, the security assumption was basically the assumption was more or less if I give you a lot of encryptions of 0, which are polynomials that evaluated at S are very close to even integers. You can't distinguish that from just a bunch of random polynomials. But now I'm giving you also quadratic polynomials with sort of a similar property. And I'm saying still, it should be hard for you to distinguish whether these are just random polynomials or have this property with respect to some s. Okay. So summing up, so we addressed we handled degree reduction from quadratic to linear, but now what about the noise? So this is sort of a recap of the noise. Adding to ciphertext doubles, and multiplying multiplies by some polynomial of n. So basically you can do a depth D circuit of add and AND gates, and you'll blow up the noise by a factor of no more than some polynomial in n to the dth power. Which means that if you start off with fresh ciphertexts that have noise that is less than inverse poly n to the d, then you can evaluate depth D circuits correctly in the sense that the epsilon will not be bigger than 1/2. So you can determine which integer you should be closest to. Right? If that wasn't the case, if epsilon blew past 1/2, then that would mean that your ciphertext noise has corrupted the signal inside the ciphertext. All right, but now we're stuck, right? What do we do now? So we've evaluated the D-depth circuit. Are we just stuck? We can't do any more operations? Is there any hope? Yes, there's still hope. Okay, so can we refresh a noisy ciphertext? So far we can evaluate bounded depth circuits, which is, it's nice. What that means is that you start off with some messages and you stick them in, you evaluate them homomorphically, and you get an encryption in this red box of the function applied to those messages. I've made it red because it's really noisy at this point and we can't do any more operations. We're kind of stuck, right? Okay, so we have this noisy evaluated ciphertext C. And what we would like to do is to get a less noisy ciphertext that encrypts the same thing, so that we can do more operations until the noise gets bad again. And then we refresh it and we can do some more operations. And then we refresh and then do more operations forever. A silly way to refresh a ciphertext is just to decrypt it and just generate a totally new encryption of that value. So that's pretty silly because you need the secret key to do that. And the whole point of homomorphic encryption is that you don't want to use the secret key to do computation on the data inside. You want to do it while it's encrypted. But something similar actually works. So what you do is you encrypt the secret key and you use that. And inside the evaluation algorithm, you run the decryption circuit homomorphically using the encrypted secret key and kind of like an encryption of the ciphertext, which is kind of like a double encryption. So you take the ciphertext and you decompose it into bits and you encrypt those bits, and you take the bits of the ciphertext and the bits of the secret key. You run the decryption circuit homomorphically on all of this stuff. And what should you get when you apply decryption to a secret key in a ciphertext? The message. So you'll get a new encryption of the message, all happening inside this homomorphic evaluation, which occurs inside the encryption box. So I kind of, I have a picture for this, so I'll just say the same thing kind of again. So what we do is we have a ciphertext that's really noisy, okay? And then we consider this circuit, which is basically like the decryption circuit, except I've just hardwired the ciphertext into the circuit. Normally the decryption circuit expects the secret key and the ciphertext as input. I'm just going to go ahead and hardwire this ciphertext that I want to refresh. And now it just expects the secret key as input. Okay. And let's suppose that circuit is a low degree polynomial, lower degree than what the homomorphic encryption scheme can evaluate. So we said it can evaluate depth D circuits. Okay, so let's assume the decryption circuit is less than depth D. Okay, so the decryption circuit is within the homomorphic capacity of the scheme. All right. And then thirdly, we're going to publish encryptions of the bits of the secret key. So, and this is what we're going to do. So here are the encryptions of the bits of the secret key. They're a nice little green box because these are fresh encryptions, right? Very low noise. Now, I'm not going to try to do any more homomorphic operations on the ciphertext. Instead, I'm just going to create this circuit out of the ciphertext, okay? I'm just going to use it to create this circuit. And then I'm going to evaluate that circuit on the secret key bits. And what do I get? Well, this is all happening inside the encryption box. I get D sub C of the secret key bits, which is decryption with the secret key at C, which is the message M, again, inside this encryption box. So I've gotten a new encryption of the same message. And the reason I've made it yellow here is that I've assumed that this decryption circuit here, D sub C, has depth lower than D. So maybe this is even less noisy than the original ciphertext, which I had done a depth D circuit on. So that's how I refresh ciphertext. So this is a new encryption of M with less noise. And again, just to emphasize, I didn't try to do any homomorphic computations on the ciphertext because that was just a lost cause, right? Instead, I did them only on fresh encryptions of the secret key bits. Okay, so the bootstrapping theorem is that a homomorphic encryption scheme that can evaluate its own decryption circuit can be used to construct a system that can evaluate forever. And just for fun, I have a very belabored physical analogy even for this. So imagine that Alice has some glove boxes that she ordered, and of course they're defective. So what happens is that when the worker is working, after he works for a minute, the gloves get really stiff and he can't do any more. Hopefully you can see the analogy, the comparison to the scheme where you have an encryption scheme that can do only so much, and then you're kind of stuck, right? So, but of course, some complicated pieces take 10 minutes to make. So if you have boxes that only work for a minute, how do you make a piece that takes 10 minutes to make? Well, okay, now I'll make some very contrived physical assumptions. First, let's just suppose that you can put one box inside another. So these are all kind of flexible boxes. They have little slots, like, kind of like the post boxes. You can kind of stuff a box inside another box, right? And let's say also that if the worker is operating inside the box and there's a key inside that box that he can grab with his gloves, and there's a lock inside there, because you just put another box in with a lock on it, it takes 40 seconds to unlock that box, after which you can take out the stuff of the second box inside there and do some more operations for another 20 seconds. So I kind of got ahead of myself. This is exactly the solution. So if you have a piece that takes 10 minutes to make, she gives the workers a bunch of boxes like this. So again, the worker sticks his hand inside. He does all the operations on the ring that he can until he gets stuck. Then he takes that box, he stuffs it inside the second box. He takes his hands out, puts his hands inside the second box, grabs the key that's already inside there, unlocks the box that he just stuffed in, takes the stuff out, works for 20 seconds, and then keeps going like this. It's a physical analogy. It's a little hard to understand because it seems like you have a lot of boxes getting in the way. But with information, it works a little better because you can kind of make stuff disappear. But anyway, that's the idea. Okay, so yes, here's my animation. Okay. So this works as long as the homomorphic, sort of the amount of work that the worker can do inside the box exceeds the time it takes to unlock a box, basically. So all right, so to sort of sum up, if you have a scheme that's kind of bootstrappable, in other words, the homomorphic capacity of the scheme encompasses the decryption circuit, then you can get unbounded HE. I didn't get into exactly how it is true that when you take the Regev encryption scheme, you know, I showed the homomorphic capacity of the scheme, but I didn't get into the decryption circuit for the scheme. It's a lattice-based scheme, so decryption is kind of like a dot product, and then some rounding to remove the error. So these are all pretty simple operations. So there are ways to make it so that the decryption complexity is within the capacity of the scheme. But like I said at the beginning, all of the schemes, with one exception, kind of follow the same framework, and it would be really nice to find something else. The one exception is a scheme that uses something called indistinguishability obfuscation. I won't get into that, but suffice it to say that the scheme is much more computationally complex than this one. It is a new framework, so it's interesting, but ideally, I would like something that's also efficient so that it can be used. Okay, so where have we finally arrived? If we look back at this diagram, so now hopefully you can understand how these box plus and box times operations are not simple additions and multiplications. Instead, what you do is you take the two input ciphertexts over there, you refresh them, and then do the addition or multiplication. So it's a complex operation. And it almost appears as, you know, as if this entire process sort of, you know, at the end picks kind of like a pseudo-random ciphertext that encrypts the right value. Because this process is so complex and cryptographic, it's almost as if it's doing some pseudo-random choice of a ciphertext from the right cloud. So again, I ask you, can we do unbounded homomorphic encryption in a different way? All right, thank you.
Thank you very much. Are there any questions? Maybe I have a question. So it looks like there's a trade-off, presumably, between bootstrappability and security. So, I mean, concretely, where are we in that kind of trade-off?
Actually, yes, that's a good point. So you need, on the one hand, to get the decryption complexity within the homomorphic capacity, you sort of have to expand the homomorphic capacity to an extent that maybe you need a really small epsilon to begin with so that the initial LWE problem is kind of easy. Fortunately, that's been pretty much resolved in the sense that there is a fully homomorphic encryption scheme that they managed to get it down so that the epsilon is basically as small as you would need just for a regular encryption scheme. There's just a way that you can control the noise so severely, basically, so that it's almost additive, so that you don't pay much in the noise for doing a very complex circuit. And so you can get that epsilon down to be inverse polynomial instead of something like inverse super polynomial, where the problem would be easier. So that problem has mostly been resolved. That particular scheme is not the most efficient. So if you want more efficient schemes, then they still have kind of slightly have that super polynomial parameters for LWE.
I have a very, very naive questions. So how much stronger do you expect the quantum computers to be?
Yeah, I feel like I'm more wary of most people in lattice-based cryptography of claiming that lattice-based crypto is secure against quantum computers. You know, I don't claim to know the limits of quantum computers, but I've certainly tried. You would think that since quantum computers are good at Fourier transforms and that sort of thing, that you could attempt that on a lattice, which is basically a grid of points, and you would expect that maybe the Fourier transform to behave kind of nicely, but people have tried such things and it just doesn't seem to work. So where that will end up, I don't know.
Craig, for a wonderful talk. Thank you.